last time we showed you that the basic Metalog equation can have any number of terms. And the example I just showed you with the Weibull distribution was a 9-term Metalog, which has 7 shape parameters. So it can capture most anything. But there are a wide range of applications where we use only the first 3 terms of the Metalog equation. Those are what's highlighted here in yellow, and that's equivalent to setting the coefficients for the other terms to 0. Now, let's talk about the 3-term Metalog. I mentioned this last time, but just as a refresher, the 3-term Metalog has that basic equation as a quantile function. That's x as a function of y. And if you differentiate that with respect to, and that is basically the CDF expressed in quantile function form. But also if you differentiate it, dx dy, and then take the reciprocal of that, you have the PDF in a simple closed form. So every 3-term Metalog has a simple CDF and a simple PDF, and one of the advantages of the quantile function form is this variable y here, which is the probability on your axis, is a variable that you can basically you can put it in a random variable, a random number generator off a uniform distribution, and then simulate easily values of x if y is a random number. Okay, so that's the basic equation. Now, as we discussed last time, there's a fundamental relationship between these A coefficients, which would be quite difficult if you need a way to estimate these from data. And what we showed last time is that if, for example, if you have 3 points on the cumulative probability distribution, and you can see those 3 points here, you can have a 3-term Metalog that will go through those 3 points exactly, not approximately, it goes through all 3 points exactly. So you can make those points whatever you want within feasibility limitations that I'll mention in a minute. And you'll get a nice smooth Metalog distribution that goes through it. Now, in terms of terminology, I want to clarify something, and that is the x and y, those 3 points, the x coordinates and the y coordinates of those 3 points. Together, I call x and y quantile parameters because these are the parameters of the Metalog distribution. We ordinarily don't parameterize the Metalogs by mean, variance, skewness, and other things, although we'll show that there is a way to do that. But I'm going to call those quantile parameters. The x coordinates by themselves I'll call quantiles, and the y coordinates by themselves I'll call symmetric percentile triplet probabilities. What I mean by that, this is a term that was come up with by Eric Bickel, and one of his graduate students at the University of Texas came up with this term in a paper they published about 5 or 6 years ago. But what it means is that your first of all, it's a triplet, so there are 3 of these probabilities. Secondly, they are symmetric around the median. The 0.5 is the median. And then if you have a 10%, then you must have a 90%. And they're symmetric in that sense. If you had a 0.05 up above here, then you'd have a 0.95. So I'm going to give myself a laser pointer here. Then you'd have, if you had 0.05 here, you'd have 0.95. But they need to be symmetric around this median. The reason we do that is because it causes various members of this matrix to be 0, and that involves finding the A coefficients as a simple closed form of x and y, of the quantiles x, and the alpha, which is the probability difference here from the median. So I'll show you exactly that. Of course, it generalizes to ordinary least squares. If you have lots of data points, you can always fit a Metalog to it, including a 3-term Metalog, but I'm not going to focus on that today. We'll focus on that kind of application more in the next session.